Good afternoon and welcome to the Computational Science Colloquium series. Today I have the pleasure to welcome Professor Efstathios Charalampidis, who is going to talk to us about one of his adventures in applied mathematics.
A lot of adventures. Thank you, Jose. Thank you very much. Thank you all for coming today. I should begin with an apology in the sense that I was hoping to show you some very, very recent progress on how to approach problems that have symmetries and how you can improve convergence in Newton's method, but I hope I'm going to have time at the very end just to touch a little bit upon that and show you what is the effect of those techniques in order to establish robust convergence in Newton's method. But this talk is all about a broad array of results over the years, as the title suggests, adventures in applied mathematics. So what I'm interested in is about complex nonlinear dynamical systems, and especially phenomena that are of wave nature. So in the first part of the talk, we're going to talk about those type of phenomena, and we're going to focus on specific types of wave phenomena coming from extreme events in the ocean, but also they can appear in optics, namely those are called rock waves, but also phenomena that involve waveforms that over the time evolution, they can actually develop singularity. So that's going to be the collapse of matter waves, or waves that actually appear in atomic physics. Then we're going to bring forth some fundamental nonlinear wave models. We're going to pose one of the key aspects there, that it is integrability, in the sense that if I have a nonlinear PDE or a nonlinear lattice system, if it possesses an infinite number of conserved quantities, I can construct explicit solutions, but that's not the case in reality. We don't have integrable systems, so we have to bring forth computational techniques. And now that brings me to the second part of the talk, namely, if I want to find standing waves or traveling waves or any type of waves as stationary solutions to a problem, I have to bring forth root finding methods, simply Newton's method. But also in those problems, it happens that we have a free parameter that you can think of this as your speed of the wave, or maybe the frequency of a time periodic solution. So that's that by itself requires the tracing of solution branches as this parameter changes. So that actually is all about numerical continuation techniques. Then a method that we employed back in the 2017, and then that was actually the starting point for a sequence, for a 2, 3, 4 works, I would say. It was the deflated continuation method, which is kind of a penalty method that allows you to factor out solutions that you have found previously. So combining now everything, we're going to focus on performing a bifurcation analysis, essentially how the stability of my solutions under perturbations can change. And that actually will reveal multiple solutions to nonlinear syndicate systems. Those systems are coming from atomic physics. Also rock waves in discrete models, integrable but non-integrable as well. And also at the very end, we're going to see how those techniques can be applied in order to find collapse waveforms, those solutions that blow up in finite time in NLS type of equations. And then I will summarize and present you some future directions of that. So wave phenomena, we're talking about disturbances that propagate in space and time. You can think of a raining droplet that falls on the surface of a pond, creating ripples that propagate over space-time. You can also think of wind blowing the surface of the ocean, creating ocean waves. My apologies about the headings there. On my laptop, they appear fine, but I think something with the connection aspect ratio, it doesn't matter, but that's about ocean waves. You can think of waves that appear in the macroscopic scale, namely gravitational waves, but also in the micro world, where you can have a beam of light that encounters an obstacle, and then it undergoes diffraction. Essentially, it gets split into different frequencies, different colors, if you like, but also based on what we know and what we call, in fact, in quantum mechanics, the particle wave dualities, that a subatomic particle can behave as a classical particle, but also as a wave. That is essentially the key ingredient for the development of quantum mechanics. So here is an example of a complex wave, which is a wave that is gigantic. It could be quite catastrophic. It is called a rock wave or an extreme event or a rare event that have a characteristic that they seem to appear out of nowhere and disappear without a trace. Okay, so this is, in fact, one such gigantic wave that was captured near the coast of France. It is a massive 160 feet high wave. Okay, so those could be quite catastrophic because instead of having a lighthouse, if you have an oil rig, you may want to know what are the conditions that such waves can actually form, so you can prevent environmental catastrophes, for example. However, there are waves that they obey, if I may, a rule that has to do with the balance of two fundamental forces in partial differential equations. Namely, in many partial differential equations, we have what we call as dispersion. You can think of this as a phenomenon that tends to spread things out, but also nature is nonlinear, so we have nonlinearity effects, and nonlinearity effects tend to focus things. Okay. Now, if you have a balance between the spreading and the focusing, you can create what we call as solitons, which are localized waves. They have a characteristic length scale that can propagate undistorted in nonlinear dispersive media. So they have appeared in practice, in fact, in optics experiments back in the 1980s. And here you can see that as we increase the intensity of an incident beam, essentially the nonlinear effect starts becoming more important. Then you have the formation of a localized pulse. Those can have multiple applications, chiefly in optical telecommunications, where people quite recently, they can actually create a burst of such solitons, and those could be used in transmission of information. Based on their stability, however, if those solitons are unstable, in some cases they can form what we call as a point singularity, meaning that the width of the wave goes to zero and the amplitude goes to infinity. That is an example of a collapsing wave, as shown here, but still it can have applications in LiDAR experiments that people can measure pollutants in the atmosphere by bursting such kind of unstable waves. They can create filaments, and based on the backscattering, they can actually measure concentrations of pollutants in the atmosphere. Not only that, but also they have applications, such filamentarily structures can have applications in neuromorphic computing, where we can try to mimic how our brain works, where we can establish synapses by actually transmitting such filaments in a network. Okay. Now, another type of wave phenomena has to do with atomic physics, or if you like, those waves are called matter waves. And it comes from the following scenario that you have a collection of particles. You can think of them as bosons, particles that have an integer spin. And if I cool them down to 0 Kelvin, then all those particles occupy the same energy, the same energy state. So macroscopically, I can make my life easier by describing this phenomenon by just one unknown function, wave function in quantum mechanics, if you like, because it describes essentially a wave. That was predicted back in the 1920s, but 70 years later on, people developed the necessary machinery in order to observe them experimentally, and that was actually the 2001 Nobel Prize in Physics. So that is the Bose-Einstein condensation. As you can see in the pictures, I have a collection of those particles that as I cool them down, then everything condenses, everything becomes localized, so I can think of this as a solitary wave or as a matter wave. Okay. They have many applications in superfluidity, in superconductivity. Essentially, you have zero viscosity, so you can test all aspects of quantum mechanics there. This is a very interesting test bed for testing all hypotheses in quantum mechanics. Even for collapsing events in the realm of matter waves, in 2D, if you pick your fundamental solution there, which is essentially a bell-shaped solution, like so here, and you evolve it forward in time because it is unstable in the two-dimensional case, it actually develops a singularity. And as I play the game with the interaction coefficients between the atoms, I can actually create those individual spots, those individual filaments. So those have been observed experimentally. Okay. So moving forward with what are those fundamental wave equations that can describe such phenomena, either stable, unstable, and so on. One of the first, to my knowledge, nonlinear partial differential equation that appeared in the literature is the well-known Kurt-de Vries equation, which has a lot of applications in solid water theory. So the solution itself describes the high displacement of the water surface from the equilibrium. Here you have a third order dispersion term, which is characterized by the third derivative. You have a quadratic nonlinearity. And the model itself is integrable. I'm not going to jump into the details about Lax pairs and so on, but we can write down explicit solutions, explicit traveling wave solutions that are characterized by the speed of the wave c. It's a hump, if you like, that moves in space without changing its shape. It has an infinite number of conserved quantities. I think I will need an infinite amount of space to write them all, but I'm just writing the first three. So it conserves the mass, the momentum, the energy, and you can construct as many other conserved quantities your heart wishes. So now, in the realm of atomic physics, the model that describes Bose-Einstein condensation in free space, and now I'm just speaking the one-dimensional case, involves now a second-order dispersion term, a cubic nonlinearity. It is integrable regardless of the sign of gamma. Gamma can be plus or minus 1. If it is minus 1, it has an explicit solution that it has this form of a hyperbolic peak, and again, you have a bump that propagates in space without changing its shape. But also, if gamma is plus 1, you have another explicit solution that is described by hyperbolic tangent, and that is known as the gray solidum, that again is a traveling wave. And if its speed, namely the value of b, goes to 0, then that actually morphs into what we call as a dark solidum. So that waveform will become a standing wave. This tip is going to actually touch the x-axis. And if I think of quantum mechanics, I'm measuring the modulus square of my solution because that connects with the probability density there. So I can think of having atoms on the left, atoms on the right, and then I have a density dip. So it has some sort of darkness there, if you like. That's why people call it dark solid. Now, on top of the NLS with gamma equals -1, there are solutions that can potentially describe those rare events or extreme events, or if you like, wave solutions. The solution is given there, parameterized by alpha, and depending on the range of alpha, you can have different localization there. If alpha is less than 0.5, you have a structure that is time periodic solution, spatial periodic solution that is known as the Ahmediev breather. If alpha goes to 0.5, at that limiting case, you have an isolated pulse that is known as the Peregrine solidum solution, whose spatial temporal evolution is shown here. If you can think of this, if this is my time direction from negative to plus, it is a wave that appears out of nowhere and then it disappears without a trace. Now, if alpha is greater than 0.5, then you have another type of such an extreme event that is known as the Kuznetsov breather. It is a time periodic solution. It has all those multiple peaks that are also candidates of such type of wave phenomena. However, the same situation persists in the discrete realm. So suppose that you replace your continuous variable x with a discrete one, and then you say that the distance between my grid points is equal to 1. So I have a pure discrete model that has a lot of applications in optics. Its n corresponds to a specific waveguide in optics, okay? So the standard discretization that people can think of is coming from finite differences, and you can pick the second order accurate finite difference approximation for the second derivative with lattice spacing equal to 1. So now that is your discrete dispersion term there. But the model turns out, the discrete nonlinear Schrödinger equation, that model is not integrable. It means that I cannot establish this infinite number of conserved quantities, or equivalently, no exact solutions. However, back in the 70s, Mark Ablovitz and his student Ladik, they came up with an integrable discretization of the NLS by averaging the wave function at the end side that appears in the nonlinear term. That model now is integrable, and on top of dark, bright solidums and so on, it has also the Peregrine solidum solution. That's the discrete analog of what we saw previously, and also its time periodic variant, the Kuznetsov breather. Okay, so those now are explicit solutions. Now, what happens now if we do something more realistic? Let's say that my nonlinearity is not cubic, it is something arbitrary. Let's say I have mod psi 2 to the power of sigma, and sigma is not necessarily equal to 1. It could be 2, 1.5, and so on. The NLS is not integrable. So no explicit solutions. The NLS now with an external potential is especially important in experiments. When people conduct those experiments for matter waves, they use an external potential to confine the atoms in a specific region in space. So when you add this extra potential, the model is no longer integrable. In that context, it's called the Gross-Pitaevsky equation. It's the NLS plus an external potential. The DNLS we encountered, we saw this in the previous slide, but also the KdV with a generalized power exponent is no longer integrable. So no solitary waves available analytically. So whatever you do in all those models and many others, if you want to find solutions to those, you have to write the problem on the computer, which means that you have to bring it into a form that is discrete so that the computer can understand it. So you have to discretize there, pick your favorite one. But all in all, you're going to end up with a root finding problem. Okay? So in that root finding problem, you have to solve a nonlinear equation, but it's all about solving a system linear equation. So your PK, your correction that you update your current iterate until you convert in some sort of norm, usually the infinity norm on the correction. Now, if you want to do one more step further, if you want to study the stability of those structures, you have to linearize your model around the solution that you found, and typically you end up getting an eigenvalue problem. Okay? So your lambda is going to be your eigenvalue, your V is going to be the vector associated with that eigenvalue. Okay? So what you want to do is you want to trace, you want to study the stability of those solutions, but also you want to bring forth numerical continuation, which will allow you to trace branches of solutions as one or maybe more than one parameters of your model changes. So crash course on the numerical continuation is that I have a parameter in my model that could be the wave speed, it could be the frequency of a time periodic solution or period, you name it. And I want to find solutions as this parameter varies. So I'm calling this parameter lambda because it's very usual. I know that it appeared previously as an eigenvalue. People in continuation, they just use lambda. Okay, I'm just following the convention. So the natural approach that you can do is that if you know your solution at some parameter value lambda naught, and you know x naught, if you want to find the solution at a nearby value, let's say lambda 1, that is delta lambda far away from the previous point, you construct the tangent predictor, essentially. So you solve this problem. So you have essentially your Jacobian with respect to your state variables. Here you have the Jacobian with respect to your parameter. You find this tangent vector, okay? And then you construct a guess, okay? x10, that this is your solution that you knew plus that tangent predictor plus the delta lambda, the increment in your parameter lambda. That works most of the cases, but it will fail when you encounter a turning point. So if you have a vertical asymptote, in that case, this problem is no longer solved. So you have to do something else. That something else has to do with reparameterizing your problem in terms of arc length, the arc length that we learned in the calculus course. So now, what you're trying to do, you don't have your tangent predictor, your x naught dot, but now you embed your problem in an n+1 dimensional space. So now you include the parameter as your enhanced space. So geometrically, what you want to do is that you have your solution branch, okay? And you're trying to find essentially the point of intersection of the solution branch and the plane that is now intersecting the screen, but its orientation is specified according to the tangent vector in this n+1 space that is essentially the normal vector to that plane. So mathematically speaking, you solve a couple problem, your original root finding problem for some parameter lambda 1, and now this one is essentially the equation of that tangent plane. So in calculus, we had that A, B, that specified essentially the components of that tangent vector, and that is in fact that tangent plane equation, okay? So that is capable of bypassing turning points. So as an example, I'm just picking a scalar problem. I have a parameter lambda. I'm using an initial guess. I do my arc-length continuation. I can bypass this turning point using this method. But then the question is, are there more solutions to my problem? If you have ever worked with fixed point methods, maybe you have played with different initial guesses, and you might have been lucky and you found another solution and you started getting excited. But then you have to use again continuation method to find other branches from your problem. Okay? But here the problem is that how can I systematically trace disconnected branches of solutions as is showcased in this problem? And the answer is that this could be done by bringing forth this idea of deflation, of this penalty map. So essentially what it's all about is that I have a nonlinear problem with this parameter lambda. I'm fixing lambda. I'm finding one solution. And then if I want to explore the possibility of finding more solutions to the problem, I no longer solve f of x equals 0. I solve m times f equals 0, where m is this deflation operator that involves two terms. Okay? So this is 1 over the norm of x minus y to some power of p plus a shifting term. The very first term acts as a repulsive potential. So if your Newton's method is close to x1, that actually will push you away from that root. Okay? But you don't want to go too far, because if you go too far, that term essentially is going to become close to 0. And 0 times f, you may erroneously converge to something that is not a root to your problem. So that's why you add this shifting. So nominal values, that there is not a standard approach how to calibrate those two. Sigma equals 1, p equals 2, or p equals 1. You have to calibrate those and see how your convergence goes. So as soon as you find a new solution, then you can recursively multiply your problem with many more such deflation operators until, for that fixed value of lambda that you have, your Newton's method no longer converges. So you declare glory, you go home, and then you say, well, next day I'm going to try another value of lambda. Yes?
In practice, does the sigma term of m, is that also very close to 0, just to keep it away?
It's sigma has to be of order 1.
Okay, cool, thank you.
Sigma has to be of order 1, right? So in the previous example, so here I'm cheating because I know that I have two disconnected branches. Now I'm going to start with lambda equals -8. My initial guess is this -0.1. I think if I use this initial guess, I'm going to converge to this root because I'm very close to this point. So as soon as I find the solution, I'm going to deflate it. I'm going to find the second solution down there. Now, the next day, I'm coming back to this and I start changing lambda. So I'm going to start moving towards positive values of lambda. And the teach value of lambda, I keep deflating those two solutions until at some point, when I'm going to deflate those two, since my problem has one extra solution, I'm going to find the other. And then I can trace such kind of disconnected branches, right? Now, for us who do bifurcation analysis, essentially, we want to see how the stability of the solution changes as a parameter changes. This is an example of a pitchfork bifurcation. We can actually trace such type of bifurcations in nonlinear wave problems. And the first one that I'm going to pick is the matter waves, where I'm considering the NLS now, the time-dependent one, and the problem is self-adjoint. It has a Laplace in there. I can look for standing wave solutions. I can use separation of variables. In other words, separating space and time. I end up with a nonlinear boundary value problem, stationary one. And now, since I want to use fixed point methods, I need a good initial guess. So how I'm going to start finding solutions? Well, you're lucky here because this is if the nonlinearity is not important in the problem, namely if the interaction in this cloud among atoms is not that strong, you can actually neglect the nonlinearity. And what you end up getting, you get a Stirling-Liouville problem. This is a classic problem in quantum mechanics that we can solve it analytically in any dimension and in any coordinate system. So you can, in fact, solve for mu and psi. You're going to find essentially the eigenvalue where nonlinear states bifurcate from, and also psi, the eigenfunction, which will be used both as your initial guess in your nonlinear solver. Then if you want to study the response of perturbations in your psi knot, in your solution that you found, you in fact linearize your equation, and what you end up getting an eigenvalue problem of this form. So The lambdas that you're going to find here play an important role in the stability of the problem, as we're going to see in the next slide. So we use this method. We pick the ground state, the lowest energetically state that bifurcates according to the parameters of this paper. We found this ground state. This is the ground state. This is essentially a Gaussian type. We continue it all the way to larger values of mu. And when you increase mu, the number of atoms, by the way, the mu is called in this context the chemical potential that is associated with the number of atoms. You keep pumping atoms in that condensate, and then your solution becomes fat, right? Then at that value of mu, we started using deflation. We found a solution that has one vortex. Essentially, this is the dark soliton if you rotate it by 360 degrees. Then we found another solution that has two vortices, solutions that have one stripe in the middle, and many, many others that even have three vortices in between. So now the coloring here highlights the stability of those solutions. In the previous slide, when I mentioned the eigenvalue problem, if those eigenvalues sit on the imaginary axis, that means that your solution is neutrally stable. Okay? So if I perturb it, my solution actually is going to go back to the solution itself. Instabilities can appear as pairs or as purely real, in fact, pairs. So this positive real eigenvalue will highlight an exponential growth in your dynamics. So that means that your solution is exponentially stable. But since the problem is Hamiltonian, it preserves the energy, eigenvalues can appear as coordinates. So you have an exponential growth, but also oscillations. Okay, so that is an oscillatory instability. So that was in fact the benchmark to connect known results using this method. And in fact, we found another 63 solutions, including 15 brand new ones. A subset of those are shown here. And many of them are coming from the linear limit, some other coming from bifurcations of other solutions. And in fact, as we can mention here, that for this branch, for example, this is the ground state, this is the first excited state. In the first excited case, you have two solutions that can come from the linear limit. One is a dark soliton stripe, as is known, it has a zero density here, and then the other one is a vortex solution. So as I keep increasing the value of mu, the vortex itself, nothing is coming out of it, but for this solution, there is something that happens here that gives birth to a solution that has now two vortices in between. And then later on, there is another branch that involves those three vortices. Those are examples of what we call as Pittsburgh bifurcations. Okay. Now, we also did this in 3D. We got really excited back then, and we found a plethora of solutions that involve now vortex lines in 3D, vortex line stars, even more complicated solutions that haven't been reported before. All of them are unstable. Okay, all of them are unstable, but they're weakly unstable, meaning that the growth rates of the eigenvalues are not that large enough that they have a potential to be observed in experiments in specific time windows. I'm not sure, and I'm not aware if experimentalists have tried any of this. Even bifurcations in 3D. So here you have a solution that has a vortex line. So this is now the generalization of this dark soliton that I show you in 3D, and the planar dark soliton. So this is a solution that bifurcates from this with such a Pittsburgh bifurcation. Now, in the rogue waves realm, we can also use those techniques in order to explore the following problem. Remember that the discrete nonlinear Schrödinger equation is not an integrable model, although it is the primary vehicle for optics experiments. So people who work in optics, they want to know what kind of structures we can observe in experiment. So what we did is that we constructed a model, or I would say that we used a model that is known as a Salerno model that interpolates between the integrable case and the non-integrable case. And in fact, this parameter that calibrates those two regimes is this G. When G equals 1 in the model, you get the integrable case, the Ablovic-Zlatic or AL. When G equals 0, you do get the DNLS. So what we wanted to do was to see whether Rogue waves in the form of a time periodic solution do exist at the DNLS limit. To do that, we consider a Fourier time ansatz, where the Fourier coefficients are those phi and m. You plug them into your model, and you get a root finding problem now in space, discrete space and time. Your m are your temporal modes. If you want to study the stability, same stuff. You perturb your time periodic solution by some perturbation that is captured by this Cn, the eigenvector here. And then what you have to do is that you want to come up with the evolutionary equations for this perturbation. Now, this one actually helps in constructed what we call as the monodromy matrix, whose eigenvalues gives us the Floquet multipliers. The eigenvalues essentially for time periodic solutions that we can say something about their stability. Now, if you want to be a little bit cautious, you can do an analysis of what we call as a plane wave. So those Rogue wave solutions sit on a finite background. Okay, you can think of this as the surface of the ocean. So what is the stability of this flat background without anything else? Is the stable solution or not? You can do some analytics here. You can perturb your background solution with amplitude q, and what you can get is an equation that connects the frequency of the perturbation and the wave number q of the perturbation. Okay, so here is a comparison between the Floquet multipliers that come from a such time periodic solution with what you get from your modulation and stability analysis. You see that first of all, the solution is unstable because you have in Floquet theory, when you have eigenvalues that are off the unit circle, that means that you have an unstable solution. And here you have an instability, you have a band of real eigenvalues that are very close with the MI prediction. Now, you have some slight perturbation because you try to compare a solution that is completely flat with a solution that is flat, and there is a localized solution on top. So that mounting creates a slight perturbation on the eigenvalues. But that convinced me enough, this is convincing enough for me that the analysis is consistent. Now, what we used arc-length continuation starting from the z equals 1 limit, with a hope to go all the way to the non-integrable case. And in fact, that was the case. We were quite successful in this, and we got a solution for the DNLS case. This is a Rogue wave solution, if you like, for the discrete nonlinear Schrödinger equation, a non-integrable model that hasn't been found before, because you cannot have an exact solution. The solution, instead of sitting on a flat background, it sits on this oscillatory background. This is known, such type of structures are called nanoptera in the context of traveling waves. And that is still an open problem on whether we can find solutions on a flat background for the DNLS. We have done some progress recently where what we consider was the following. We picked this Kuznetsov breather, this Rogue wave, as an initial condition in the Ablovic-Zladek and the discrete nonlinear Schrödinger equation with a small background amplitude. And we monitor the evolution at the central site. The evolution seems to be quite close to one another, although there is a phase shift. But that suggests that both models, when Q is small, they are very close to one another. That, in fact, was quite useful because we picked that solution as an initial guess to our Newton solver for the DNLS, and we were able to find now a solution that sits on a finite background. So that was quite interesting to see. And in fact, it is a known time periodic solution for many periods. Okay. And even more, when we try to, I went too fast. And even more, if we try now to increase the background amplitude Q to larger values, that flatness starts getting destroyed. So it's still an open problem that we don't have an answer about how we can construct such solutions with a flat background for non-integrable systems. So this is an open problem. Now, in the defocusing realm, so if in my nonlinearity, I have the opposite sign, such KM breathers do exist for the Ablovic-Zladek because it is still integrable, And that is a recent work that appeared last year with Barbara Prinari and her group, that they are experts in inverse scattering and Lax pairs. And the very interesting thing that we observed was that even though solutions are unstable, we haven't seen before the emergence of blow up. All those solutions, if you evolve them forward in time, they blow up, which is quite bizarre. Quite bizarre, and we are trying to understand why this happens. Although, if you see, the conservation laws are very well satisfied over the course of the evolution. Now, that brings me to the last part of the talk. So how much time I have? 10 minutes?
Much as you want.
As much as I want? Okay, John said as much as I want. That's not the case, John. I'm sorry. Okay, so that brings me now to the last part of the talk, which is about blow-up phenomena. So what I'm going to focus is the NLS again, non-integrable model with a power law nonlinearity. Now sigma is no longer equal to 1. It could be greater than 1 or less than 1. But surprisingly, this NLS has an exact solution. Okay. And if you do the stability analysis of this exact solution, the spectrum reveals the following: that sigma, if you start from the integrable case and you start increasing sigma, then at some point at sigma equals 2 and beyond, you have a real eigenvalue that actually tells you that your solution is unstable. And in fact, if you do dynamics, the solution for any sigma greater than 2 blows up. That happens because, well, the instability emerges because for the imaginary part of the spectrum, you have a band edge mode that actually starts getting decreasing, and then there is the mirror image down here that they collide, and then they exit as a real eigenvalue here. Now, the number of the zero eigenvalues that you have here, because this is a PD that has symmetries, and what I mean by symmetries is that if you look at this differential equation, if you do any shift in your variable x, if x is x plus epsilon, you have the same partial differential equation. That means that your equation is translation invariant in x, so I can grab my solution and I can move it anywhere I want. But also it has another symmetry that if I replace psi with psi times e to the I theta, that's an arbitrary phase factor, still the PD is exactly the same. So you have two symmetries. Those two symmetries appear as zero eigenvalues in your spectrum. So here you have all those zeros that sit in here. So you have in total 4 zero eigenvalues that come with a multiplicity. So if I want to find now those blow-up solutions as stationary solutions, and the reason that I want to do this is I want to study their stability. Okay? I have to consider new variables. Since my solution, its width goes to 0 and the amplitude goes to infinity, I have to introduce a new set of variables that accounts for that. So I have to rescale space in this fashion, and I have to rescale time. So if I do this, I end up getting an equation, the NLS, if you like, in this frame that co-explodes with the solution. Okay? Now, in this co-exploding frame, I'm calling G the rate of how fast the solution blows up. This is the blow-up rate. Okay? And if I want to solve this problem, okay, if tau now, if this artificial time goes to infinity, phi becomes a tau-independent solution that satisfies this problem. But now you have the issue that you have two unknowns. The first unknown is obviously your stationary solution in this co-exploding frame, but also you have an unknown parameter G, that blow-up rate. You can close the system by imposing an extra algebraic condition that allows you to determine G uniquely. We call this a phase condition or a point-wise condition or a pinning condition. We request that I want to find this phi s such that at x equals 2, it matches with the value of the solitary width. It's just an option, okay? So when you do this flow, as I said, as tau goes to infinity, this dynamics, this self-similar dynamics, in fact, quickly converts to a steady state. As you see,
at tau equals 35 or so, the solution is stationary. I'm graphing the real and the imaginary parts. The dust black line is the solitary wave, okay? And at x equals 2, I requested that the solitary wave and the and the real part of the solution, they match together. So that is the case there. And now I can use this profile as my initial guess to perform bifurcation analysis of such cell-similar solutions as this parameter varies. And here it is. Here you have the dependence of G, of this blow-up rate, as a function of sigma. The G equals 0 corresponds to the solitary wave, okay? And then, past the point sigma equals 2, the solution becomes unstable, but it gives birth to two branches. One is a branch that blows up in forward time, and then there is another branch with negative G that blows up in backward time, okay? So solutions on those two branches are shown here. One of the problems among many others is that the solutions that you have in this problem, they do not decay exponentially, they decay algebraically, which means that you have to use extremely large domains in order to match the asymptotics on your solutions. However, with the wisdom of John Chapman, whose name is kind of hidden here, who is at the University of Oxford, he came up with what we call as a dynamical system that describes this bifurcation. It's called the normal form. And in fact, we get a perfect agreement with the normal form that he predicted. So our numerics are consistent with that. Now, moving forward with the spectrum, so when you do your stability analysis in this co-exploding frame, you track all the eigenvalues that appear here, the point spectrum in particular, and those are associated or they are very close to the blow-up rate. Now, you see those jiggles here, but that has to do with the finite size computations. If you use a larger domain and even if you increase the accuracy, you just get it perfectly. Okay? So I wanna skip this because I wanna focus on something that is gonna appear quite soon in SciAm Dynamical Systems Journal. We got really excited with this one-dimensional problem because not only this solution does exist, like with one hand, and here I'm just monitoring not the real and the imaginary parts, but its modulus. You can construct systematically two ham solutions, 3, 4, you name it. All those blow up. Okay, those are coming as a bifurcation precisely at sigma equals 2, and we were able to do a careful asymptotics analysis, matching the normal form with our bifurcation diagram, but also the spectrum of those solutions. So that paper is going to appear soon. We just finished the proofs of that paper. So now that actually brings me to my summary. First of all, this blow-up business is funded by the National Science Foundation, and I'm currently extending those techniques in 2D, in 2 dimensions, which is quite challenging. You have those algebraic decays. There are all sorts of other issues that appear there because we want to do bifurcation analysis of those solutions. And in fact, when we perform the stability analysis, we want to connect the spectrum with the normal modes of the problem, with symmetries, in fact, of the problem. You may have a possibility to decrease the dimensionality of the problem by using mesh adaptivity techniques. I'm coding everything in an open source finite element software called FreeFair++, which has the advantage of using domain decomposition methods. That's in fact the topic of 6 and 5 that I picked to teach our students. The extra bit of this is that combining all those techniques with the penalization of symmetries. The convergence in Newton's method is quite nasty there. You may get to a stall, you may stagnate, no improvements, and that has to do with symmetries. I have been torturing myself, I don't know, it's been a year, with many approaches. One is using Lagrange multipliers to penalize symmetries, where you have to solve a differential algebraic problem. You have to impose some phase conditions. Lagrange multipliers work, but when they don't work, they're terrible. Number 2, there is an approach by Herbert Keller back in the 1980s who developed what is known as the bordering algorithm. that its existence emanated from the necessity of using arc-length continuation and solving the underlying systems. That also works nicely, but if you go to two-dimensional problems, if you want to do this bordering algorithm, it requires the computation of the left and right null vectors. The right null vectors in your problem, you have them. The left null vectors, you don't have them. So how are you going to do this? You have to either solve an eigenvalue problem for your Jacobian inverse, or do singular value decomposition, which is very, very, very expensive. This is an ongoing work, and we hope that we're going to address this problem. And lastly, this is now a fresh, well, not 100% fresh. It's been a year and a half as a direction, but there is a new grant that I received from the Department of Defense, from the Army Research Laboratory, to study quantum droplets, those massive quantum objects that are quite interesting in atomic physics. And FreeFEM++ with all its parallelization and domain decomposition methods and method activity will be quite pivotal in tackling problems that people haven't even thought of addressing, especially when it comes to eigenvalue computations. If you want to study the stability of those fractions, we're talking about matrices that could be 50 million by 50 million. And you may have branches of solutions that have 200 points of that. So we hope that we're going to actually make progress even in 3D. And we're really excited and looking forward to hiring 2 PhD students starting this fall. Okay. Now, here are some key references for the stuff that I told you, but I want to show you an example. I'm still connected to my workstation upstairs, so I just want to show you something in FreeFEM that computed a solution for the blow-up problem that has this issue of symmetries. So if I, let me see, oops, I turned off the sharing, I guess. Let me try again. Is it there? Okay. Now, let me see. Now, if I solve my blow-up problem, okay, it may take a couple of seconds, okay, because this is now a problem that has 8 million degrees of freedom, okay. I'm using it an initial guess, and you will see in the course of, yes, I mean, I have 8 million degrees of freedom, so maybe actually, let me press the enter so that you can see the output gradually. Okay. Of course, there is some sort of a lag because we're just connected to via SSH. So essentially, the solution that I'm trying to compute, because I have computed it, is this one. So in 2D, you may have like blobs, you may have rings. And in fact, if you remember in my talk, at some point, I showed you an experimental result of a blow-up solution that had all those spots, all those filaments. There it is, theoretically. Okay, there it is. So now it will start computing the thing, but then at some point, the iterates, okay? Now it says 10 to the negative 5. So when I see this, I start getting excited that I'm going to head towards convergence. And then you're going to see in a bit that it's going to start getting stalled. Because in your 10 to the negative 6, that's good. Is there any marker here? No? Any? No? Talk? Shall I do this there then? Okay. So that's okay. I will do this too. So essentially, in your Newton's method, what happens is that you're trying to solve this system, okay? And when your Jacobian has 0 eigenvalues, it means that you have a null space, which means that your matrix is no longer invertible. This is the case where you now hit, okay? So now it's gonna, I mean, one can say, I'm happy with my infinity norm to be 10 to the negative 11. Sure, okay. And now it will get stalled. Or maybe it will get worse, okay? It will actually maybe go back to the 10 to the negative 10, and then it will do this, as my French collaborators, they call it yo-yo, okay? You go back and forth. You see? Now it did increase. Now I'm going to stop this and I will show you if I involve the Lagrange multipliers business. Essentially, I'm penalizing symmetries, and I hope that I will have the opportunity in the future to jump into the specifics on how to solve this problem or potential way to solve this problem. Is that you can, in fact, remove the null space of your Jacobian and achieve robust convergence. So now let's see. It will take probably 30 seconds so that we can convince ourselves that this thing is working. So now I'm solving the problem, even the previous one with 56 processors. I'm requesting tolerance 10 to the negative 13. Okay. So let's actually let it run. Maybe I should. So this code employs the techniques that we started covering in 605 domain decomposition methods. That's why it is really, really fast. Now, here I'm just monitoring the value of my Lagrange multiplier. In reality, that should be 0. Okay, but 10 to the negative 13, I'm fine with that. Or 10 to the negative 14, I don't care. If it is 10 to the negative 6, that's not good. Okay, so now you see, from something that was 10 to the negative 4, it jumped to 10 to the negative 7. Okay, I think it will take maybe one more or maybe two more, and done. Okay, how long it took? 1 minute and 13 seconds. 8 million equations. Okay, so that's all. Thank you. Any questions? Yes.
So these collapsing solutions,
Yeah.
the nonlinear Schrodinger equation.
Yeah.
What do they mean physically? Does that mean that
Yeah.
probability of being somewhere collapses
To Dirac delta.
absolutely where it is in the domain?
Yeah. To just a point, Dirac delta. But people have seen them in experiments.
What is this
Pardon?
relation to this? What does it imply for like uncertainty?
Say it again.
What does this imply for like uncertainty principles? I mean, I don't know much about this, so I think Heisenberg, when I think about things collapsing to a point, what
Is it fair to say that this is just for the linear case, or it should apply for the nonlinear one? The accelerating
I don't
principle.
know.
Yeah, I don't know either. But the solution that I just showed you. Let me go back. Let me go back. What was that? I think it was here.
Can I make a comment?
There it is. So you see.
Heisenberg is basically you probably here. In this case, you have no idea.
Yeah.
Well, okay, so what is the value of, what is the nature of the independent variable where you are localizing this?
The independent variable.
I mean, you're collapsing.
Yeah, you conserve the energy.
You're conserving energy, but you're collapsing in some space.
You are collapsing on a single point. So everything focuses, and what happens is that the model has dispersion and nonlinearity. So when the nonlinearity is stronger than dispersion, it drives the system to focus. So it keeps focusing until you collapse to a single point, whereupon at later times, the model is no longer valid. So that is something, for example, in water waves, people are trying to solve the $1 million problem with the Navier-Stokes equation. So if you have blow up, if solutions are regular for all times. So this is an important thing to know for a model, whether it develops collapse or not. But even in such a problem, when experimentalists fire off such unstable pulses over the course of evolution, in 2D, you have the emergence of those filaments. Those don't have an infinite amplitude, but they have a gigantic amplitude. And what I show you in this very last, this one, I would like to kind of think of this.
It approaches a ring of infinite
Yeah.
strings.
Yeah. So here it is.
So I'm trying to understand all those things. So this is an experimental work that I think if it hasn't appeared, it will appear in PRL. Yeah.
How do you remove the kernel space in the Jacobian?
Yeah. Okay. So the two approaches. One approach is that in general, if you want to solve a singular system, let's say that A doesn't exist. But you happen to know two things. One is, let's say that you have nullity one, that you have one singular direction. If you know, let's say, let me call this my right null vector. And if you also happen to know the left null vector, Herbert Keller says that instead of solving this, you can solve an augmented problem this is x, and now I'm using an auxiliary variable alpha that is essentially b0 here. So essentially, what you're trying to do is that when you have a singular system, you like to think of this as my solution is a particular solution plus a scalar multiple of the right null vector.
Yes.
But in that framework, what you impose extra is that the left null vector is essentially orthogonal to my solution. So essentially, you solve the problem in the complement. That's one way to do it. The other way is with Lagrange multiplier. So now I need space. The other one is, let's say that in that problem that you have translation invariance, for example. So you write your PD plus a Lagrange multiplier times the generator of translations, which if x goes to x plus delta, that's essentially your shift in space. The generator is going to be the derivative of this with respect to x, and delta goes to 0. So the generator, in fact, is just the partial x. So you add this as a Lagrange multiplier here to the problem. But then, in order to close the system, you have to impose an extra algebraic condition. And that condition is the integral of the partial x of some reference solution. And you request that this is orthogonal with t minus u. This comes from equivariant theory. So those are the two approaches that I'm aware of. Now, here is the problem, however, is that with this approach works, but and of course, if u is a solution, you expect that this to be 0 or to machine precision. Sometimes you get lambda that is 10 to the negative 5. That has been causing me nightmares for many months. And they said, scrap this. I will go to this, but I don't know the left null vector. If you have a PDE with 0 Neumann boundary conditions, the adjoint problem doesn't solve the same boundary conditions unless you have periodic. I don't have periodic boundary conditions. So what is the way out? Maybe you want to compute the eigenvalues of this problem and pick the left null vector numerically, but you have to do this per each Newton step. It becomes very expensive. Or if you do singular value decomposition, more expensive. So I have been torturing myself a lot on this.
But you could take the eigenvalue that has associated to the largest the eigenvector is associated to the largest eigenvalue modulus. That is fast, right?
You have to pick essentially you have to track down the 0 eigenvalue because it is the 0 eigenvalue that causes the trouble. So whatever you do with Newton's method or with root finding methods, when you see that your root finding doesn't converge robustly, it means that but maybe you have a kernel there and you have to remove it. If you remove it, as I showed you, that done. Yeah.
On that note, we're going to thank our speaker.
Thank you. Thank you very much. Thank you.